Welcome to rate laws, an introduction. So, chemical reactions can be reversed. We can have the chemical reaction occur one way, or we can have the chemical reaction occur the opposite direction. So, where our forward reaction for our decomposition of NO2 looks like this, the reverse reaction then is just flipped around. So we have 2NO plus O2 reacts to give us 2NO2. So if we place NO2, the nitrogen dioxide, into an empty container, then initially only our forward reaction occurs because there is no NO or O2 present. If we don't have any NO or O2 present, then we can't have the reaction form between those two. And so this means that the reaction rate depends only upon the rate of the forward reaction. It doesn't depend on the rate of the backwards reaction, because the rate of the backwards reaction is 0. But after a while, the reaction rate decreases for the forward or for the overall process because the reverse reaction is occurring at some significant rate. And that means that now we're forming some more of our NO2. And that means that now our change in NO2 concentration over time is going to drop, because some of the forward reaction that occurs is being balanced by a backward reaction that's basically undoing the forward reaction. So at some point then the forward rate and the reverse rate become equal, and now the NO2 concentration stops changing. But if we look only at the beginning, when our reverse reaction rate is negligibly small, then we can examine the initial reaction rate. Okay? So the initial reaction rate is the reaction rate at the beginning of the reaction when just as we start the reaction to go. Now, what we ideally like to do is to measure the instantaneous rate the instant that we allow the reaction to start happening. Now, we can't really do that. We can't measure the instantaneous reaction rate. All we can do is measure a rate over some period of time, but as long as we fix that period of time to be just at the very beginning, then we can assume that the backwards reaction rate is so small as to be 0. And that's what we're doing. We're fixing ourselves to only looking at the very beginning of that reaction, when we essentially have none of our products around yet, so none of the products can decompose and form our reactants again. So, in this case, then we can write a rate law, which shows how the rate depends upon the concentrations of the reactants. So, in this case, with our NO2 reaction, our NO2 decomposition, we can say rate is equal to K times concentration of NO2 to some power N. So, this K here is our rate constant, and our N there is called the order of the reaction with respect to what's inside the brackets, so the NO2. It's the order of reaction of NO2. So both the rate constant and the order of reaction have to be determined experimentally. We can't figure out what these values are, the value of K and N. We can't do that just looking at the reaction. We have to go out and perform an experiment. In general, then the order of the reaction is a small or non-negative integer. A small and non-negative integer. It's usually 0, 1, or 2. Now, we can have orders that are negative. We can have them be fractions. We can have them be larger than 2. But most reactions that we look at, certainly most of the reactions that we look at in a general chemistry course, have a reaction order of 0, 1, or 2. So that was an introduction to rate laws.